Hi, this video is on properties of cyclic groups. There are certain properties a group enjoys if it is a cyclic group. The first property is every cyclic group is abelian. Proof: let G is a cyclic group generated by A and let G1 and G2 be any two elements of G. To show G is abelian, we show G satisfies the property of commutative. For that, we show for all G1 and G2 in G, G1 G2 equals to G2 G1. For that, we have G1 is generated by A, therefore G1 equals to a to the power m and G2 equals to a to the power n for some mn in Z. Next we take G1 G2 and that equals to a to the power m, a to the power n, that equals to a to the power m plus n, and m and n are integer and integers are commutative with respect to addition. Therefore, a to the power n plus m, that expands to a to the power n, a to the power m, and that gives us G2 G1 for all G1 G2 in G. This shows G satisfies commutative property and therefore G is abelian. The second property is a subgroup of cyclic group is cyclic. To prove this property, let G be a cyclic group generated by A and H be any subgroup of G. We have two cases. Case first, H is the trivial subgroup. In that case, there is nothing to prove. This subgroup is cyclic. Case second, H is not equal to this trivial subgroup. Now, to show H is cyclic, we find its generator. A generator of a set generates every element of the set. So we consider integer m to be the smallest such that m belongs to H. M is the smallest of all integer such that m belongs to H. We try to use m as the generator of H. For that, consider e to the power n be any elements of H. Then by division algorithm, there exists Q and R in Z such that n equals to m times Q plus R, where R equals to 0 or less than m. Then e to the power n can be written as a to the power mq times a to the power r. And because e to the power n and e to the power mq both belongs to H, by closure property, e to the power r also belongs to H. We have two cases to consider. If r is not equals to 0, in that case we have r is less than m. Therefore, we get r to be the smallest such that e to the power belongs to H, which gives us contradiction because our supposition is m is the smallest. Therefore, r must be equals to 0, and in that case we have this element is identity element. Therefore, e to the power n is equals to e to the power m q. This shows e to the power n is generated by e to the power m, and this is true for all the elements of H. That means H is generated by e to the power m, therefore H is cyclic and any subgroup of a cyclic group is cyclic.